So again, just following up from the end of the last video, most hexoses are capable of cyclizing in different manners. All right, so the most common cyclic form of glucose is the one shown right here, and monosaccharides that make a six-membered ring are what are called pyranoses. All right, so this is the pyranose form of glucose. All right, and monosaccharides that make a five-membered ring are what are called furanoses. All right, and the names derive from organic molecules that these are similar to, namely what's called a pyran versus furan. But the thing is that if you have the linear form, all right, if the cyclization occurs from this hydroxyl on the 5-carbon onto the aldehyde, you would end up getting the pyranose form, right? But if the cyclization happens where a lone pair on this hydroxyl on the 4-carbon, you would end up getting the furanose form, all right? So what ends up happening is that if you dissolve glucose in water, all right, you're not just going to have one form or the other, all right? So even though there's a preference, the solid form, you're going to have different amounts of these. But if you have it in water, about 0.25% of the glucose molecules will exist in the straight chain form or the linear form, all right? About 99% of the glucose molecules are going to exist in the pyranose form, all right? And less than 1% are going to be in the furanose form, all right? So for glucose, the definite preferred form that it's going to be in is this one right here. And if you just look up structure of glucose on the internet, you would see this is by far the most common structure that you would see. The only variation that you might see is this one right here. All right? And remember, this particular hydroxyl right here, the one that's on the carbon right next to the oxygen, could be either up or down. All right. All right. And keep in mind that even though these are the percentages, it doesn't mean that the ones that are in this form always stay that way. All right. These things are constantly interconverting. So the pyranose can open back up to the straight chain, which could either recyclize to make the pyranose, or it could cyclize to make the furanose. So, but there's just going to be a statistical distribution where it's always going to be favored towards this particular form for glucose. All right. So one last thing, and this is the one that probably affects biology the least, is that for each of these types of monosaccharides, all right. So again, these are chiral molecules. All right. We have a bunch of tetrahedral centers with 4 different groups coming off of it. All right. So if we took the most common form, so this right here would actually be alpha glucose. If this was right here was a mirror, all right, we could draw an exact mirror plane image of that molecule, all right. And again, remember what you call mirror plane isomers of materials that have chiral centers. These are enantiomers, all right. So the nice thing is that for monosaccharides, there really is only one enantiomer of the sugars that are going to exist, and that's going to be what are considered the D monosaccharides. All right. If I drew the enantiomer of this, which in its cyclic form would be this guy, all right, this would be the L glucose. All right. And the thing is that this is unnatural. You don't find this version of glucose in nature. All of the glucose that you're ever going to see in biological systems are going to be the D variety. All right. And notice that each of these is going to have their open chain variety. All right. So notice that this straight chain variety is the exact mirror opposite of this straight chain variety. All right. Notice that this OHs are on the inside. Here the OHs are on the outside. Here they're on the inside. So which other form you show these in, either the straight chain or in the cyclic form, there is an enantiomer that would exist for it. One interesting thing about L-glucose, even though it doesn't exist in nature, it can be synthesized in a laboratory. And one interesting note about it is that if you were to taste this, it tastes just as sweet as regular glucose. But the thing about it is it has no nutritional value. All right, your body, so glucose is something that your body can use to make energy from. All right, and the reason that it can do that is that your body has enzymes that are designed to metabolize this into what's called ATP, which your body uses for energy. All right, well, those enzymes are very specific to the orientations of all of these groups on D-glucose. All right, so even though this material right here tastes just as sweet as regular glucose, your body is not designed to be able to turn this version of glucose into energy. So if you recall before when we were showing cyclic structures of glucose, you remember this particular hydroxyl group, the one that's right next to the oxygen in the ring, right? We showed it as having the squiggle, which meant it could either be above the plane of the ring or back behind the plane of the ring, all right? So we're going to spend a little time talking about those two different varieties. So first of all, that particular hydroxyl group, all right, and again, here I'm showing it in its below the plane of the ring version. Here I'm showing it in the above the plane of the ring version, right? And just a little nomenclature that goes along with this. If the hydroxyl group is below, we consider that the alpha form of glucose, all right? And if it's below, above the plane of the ring, we call that the beta form of glucose, all right? The D that I put in this refers to the particular enantiomer, which we were talking about before, all right? So it's this version, this mirror image of glucose right here. That's what makes it the D, but the alpha, one quick way to spot this is to locate this CH2OH. If this hydroxyl is on the opposite side of the ring from that, then it's going to be the alpha version. If it's on the same side of the ring as that, it's going to be the beta version. So the thing to note about that particular hydroxyl group is that it arises from the carbon that is originally the aldehyde in the straight chain. All right, so what I've shown here is this is the linear form of glucose, where instead of drawing it as a straight line up and down on the page, I've shown it where it bends at the carbons, which is what, if you consider the bond angle of a tetrahedral carbon, this is what it would want to do. All right. So in drawing it this way, you can see that the hydroxyl off that number 5 carbon would be very close. So remember, recall there's an electron pair on that oxygen right there. And when this thing cyclizes, that electron pair can essentially attack that carbonyl carbon. So this oxygen right here acts as a nucleophile. The aldehyde carbon right here acts as, so this is a nucleophile. This carbon right here is an electrophile. And when that happens, that's what creates the cyclic form. All right. So the reason that we can get two different stereochemistries there is that, and it's kind of hard to see this in this model structure, is that the electron pair could attack this aldehyde from one of two possible sides. So I'm not going to expect you to understand the specific geometric arrangement for this, but just realize that if this oxygen right here attacks it from one of the sides, you're going to get the stereochemistry where the hydroxyl is down. But if it attacks from the aldehyde from, say, for instance, the bottom side of it, you're going to get the opposite stereochemistry. All right, so we'll just call them side 1 and side 2, and that's what ends up causing the different sides. All right. So the thing is, if you have glucose dissolved in water, all right. Recall earlier we mentioned that if you had glucose dissolved in water, you're going to have 99% of it that exists in this 6-membered variety. All right. What makes this a little bit more complicated is that even though 99% of it is in this version right here, of that 99%, some of it's going to be in the alpha form and some of it's going to be in the beta form. All right. So if you were to measure that for glucose in aqueous solution, of that 6-membered ring variety, all right, 64% of it is going to want to be in this beta variety, and 36% of it is going to be in that alpha variety. All right. So, and again, those two versions can interconvert between each other because, again, the cyclic form can open back up to the linear form, and then it could either cyclize the same way or it could cyclize back this other way. When it recyclizes, it doesn't have to recyclize to make the 6-membered ring. This thing right here could cyclize to make the 4-membered ring, making the furanose like we mentioned before. And so there's a lot of different combinations, a lot of different forms that glucose can have in water. All right. So one thing that's just to keep in mind is that even though glucose has this natural percentage of beta versus alpha varieties, each specific type of sugar, all right, for example, if we were talking about galactose instead of glucose, its percentages of preferred alpha and beta forms would be expected to be different. All right. So, and again, things work the same way. If the OH is going down on whatever monosaccharide that is, that would be the alpha version. If it's going up, that's the beta version. All right, and this is the reason that a lot of times when you see people draw glucose, they end up drawing that hydroxyl group, which you call, the word for that is the anomeric carbon. This is the carbon that contains the hydroxyl next to that oxygen is called the anomeric carbon. All right, which by the way happens to be the #1 carbon when you're numbering the carbons on a sugar. A lot of times when you're drawing that, you show it with this little squiggle instead of showing it either being up or down. And that's just to represent that it could be up or down, and you're not claiming this variety versus this variety. Because again, if this is dissolved in water, you're going to have this constant interconversion where you're going to have a mixture of these anyways. All right. The other hydroxyls on the ring are going to have fixed stereochemistries because there's nothing, none of this interconversion is going to affect the stereochemistry on these right here. So those are always going to be stuck in whatever orientation they are. But this particular stereochemistry it can change because of this interconversion. So one thing to keep in mind is that even though the Hayworth projection is the most common way to represent the cyclic varieties of the monosaccharides, sometimes you'll find that people will show them in what's called a chair conformation. All right, we mentioned chair conformations earlier when we were talking about stereochemistry. Chair conformations are things that you have whenever you have a 6-membered ring, and they exist because all of these members of the 6-membered ring are tetrahedral, have that ability to have a tetrahedral arrangement. Oxygen is actually bent triatomic, but it can still have that same angle that these tetrahedral carbons can have. All right, and when you do that, you're going to find that the groups coming off have different ways that they can come off. So things that are pointed either straight up or straight down, like this hydrogen would be straight down, this is straight up, this is straight down, this would be straight up off this carbon right here. Those are what are considered axial positions. Things that come out like this, all right, like this is kind of going out right here. This is coming out right here. This is coming out to the side. Those are what are called equatorial positions. And that has a big impact on the shapes that these things can make. All right. So the reason that people sometimes draw these chair conformations is it allows you to see these axial and equatorial positions better than a Hayworth projection like this. All right, notice when you're drawing these chair conformations, and I will say that it takes a little practice in drawing these chair conformations. The edge one of the edges right here you can see is drawn distinctly darker, indicating that this would be, if we had a ring, one of the sides is going to be closer to you than the other. The side that's closer to you is shown with a darker edge. The one that's going further back has got the lighter edge.